Welcome everyone. Today, I will be presenting our work titled CounterPC, Counterfactual Feature Realignment for Unsupervised Domain Adaptation on Point Clouds, which has been accepted to ICCD 2025. This work addresses a fundamental challenge in point cloud domain adaptation: how to selectively transfer domain invariant semantics while avoiding bias from domain-specific geometric variations. Our solution, CounterPC, introduces a causal framework to model this disentanglement and implements counterfactual feature generation to enable bias-reduced adaptation. Causality concerns the underlying mechanism of generation, rather than observed statistical associations. While traditional UDA techniques often align distributions based on correlations, we aim to model causal relationships between input structure, domain shifts, and target predictions. For example, in images, style and texture are often correlated with semantics, but not causally related. Similarly, in point clouds, sensor noise, sampling patterns, and domain-specific geometric distortions may spuriously correlate with the label, leading to biased adaptation. Our approach seeks to decouple these confounding factors by reasoning about interventions, how features would behave if domain-specific influences were removed. In unsupervised domain adaptation, UDA, the goal is to leverage labeled data from a source domain and adapt to an unlabeled target domain. Existing methods largely rely on aligning distributions between domains, either through adversarial training, feature normalization, or self-training techniques like pseudo-labeling. However, these methods often struggle to capture domain-invariant causal semantics, especially in structured data like point clouds. Unlike images, point clouds present unique adaptation challenges due to their local compositional inconsistency and global redundancy. Features in point clouds are spatially unordered, sparse, and often vary across domains due to LiDAR settings or object scales. This makes disentangling semantic, class-related, features from domain-specific geometric variations especially difficult. As a result, direct feature alignment is often ineffective, motivating a shift towards self-supervised learning that implicitly captures geometry-aware features. Yet, such strategies lack an explicit mechanism for causal disentanglement, which we aim to address. In our causal graph, the raw point cloud input X is generated from a set of latent variables ZC, category-relevant semantics, residual geometric variation V, unobserved confounders, sensor noise, occlusions, U, domain index. Our goal is to learn a model that captures, i.e., what the prediction would be if the structural semantics were fixed across domains, thereby intervening on domain-specific biases. This perspective allows us to go beyond domain-level alignment and reason about feature-level interventions. To mitigate the biases induced by the confounding path, we adopt counterfactual reasoning. Specifically, we ask, if the content feature Z in the target domain were structured like the source domain, how would the residual feature Z change? This leads us to model the counterfactual distribution, which enables bias-reduced residual features. To approximate this, we implement optimal transport, OT, between target domain features and source domain category prototypes. Our proposed architecture, CounterPC, consists of two main modules: counterfactual feature generation. CFG uses optimal transport to generate counterfactual residuals that align with source semantics. Implements the intervention to obtain domain-invariant joint distribution modeling via self-supervised learning. We employ point cloud reconstruction as a self-supervised task, enabling fine-grained joint modeling of This is especially suited to 3D foundation models, 3DFMs, which provide rich geometry-aware priors. Together, these modules form a causally grounded adaptation framework that explicitly disentangles structure from variation. We conduct extensive experiments on two challenging benchmarks, Point DA10 and GraspNet PC10. CounterPC achieves state-of-the-art performance across multiple source-to-target transfer scenarios. Ablation studies validate the importance of counterfactual residuals, self-supervised point generation, class prototype optimal transport. Notably, even when starting from strong backbones like Point GPT, our causal modules yield significant further improvements, e.g. plus 4.1% on Point DA and plus 5.7% on GraspNet PC. This confirms that the gains are not merely due to stronger encoders, but from principled causal design.